Hi, chemistry folks. This is the section 12.1 home edition. Um, yeah. All right. I'm going to start with just, I guess, a suggestion. I would say probably after watching this, you might want to go and watch Crash Course Chemistry number 12. Well, at least something about, we'll go to Crash Course Chemistry and see what there is about gases. They have several about gases, and next week we'll be looking at the gas laws and ideal gas laws. Yeah, so Hank's version of that might be helpful to you. There'll probably be some demonstrations about how that stuff works. Stuff I really can't show you right now because we're not in person. I don't want to do something in this amount of space right here. So hopefully you picked up your packet of stuff. With the slides. That'd be really good because that's what I'm going to go over right now. And I want to show you a few things, a couple things you're going to be doing on your calculator because there's some practice problems that you're supposed to do, but I want you to learn how to use the unit converter for pressure on your calculator. Don't worry about all the other stuff. Usually we'll get those things goofed up at some point if you don't get a little help. Okay, well, first things first then. Table of contents for this chapter. It's a pretty important chapter. We've got internal combustion engine and machines, all those kinds of things, weather balloons and pressure gauges and all kinds of stuff, boilers and what makes the world go round kind of stuff is in this chapter. So gases are super important. There's even some bad jokes we can make later when we've got what do you call it when gases pass through a small opening, so we'll have some funny jokes to do there. And here are three sections. First, we're going to talk about the characteristics of gases, which should be no surprise to you. We've been studying phases of matter and all that kind of stuff for a while, and we did it in physical science. So first section won't be too bad. And the second section will be comparing volumes, amounts of moles of substances, their temperatures and their pressures, and show how all those things are related. We'll use a couple of simple graphs of direct variation and inverse variation, where you get the curvy line kind of thing that drops down. And then we'll put it all together into the combined ideal gas laws. Yeah, where we got PV equals nRT, pressure volume equals number of moles times the gas constant R, and then PV equals nRT, temperature. Temperature will be in there too. I saw a chemistry professor that was his license plate, PV equals nRT. He liked this stuff so much. Okay, well, moving on. Here we go. Objectives for our first section here describe the general properties of gases. We're going to talk about pressure, give you the SI units for pressure, and that's important for us. We've already been looking at phase diagrams, which had pressure on the vertical axis, and those were in pascals or kilopascals or something. So we'll look at what they use in chemistry as opposed to what they might use in engineering or in physics or in different setups. And we'll use our calculators to convert between different kinds of pressure units. So the Pascal is pretty cool. I like it because it's named after Pascal, who's a pretty cool guy. And then relate the kinetic-molecular theory to the properties of an ideal gas. Remember, kinetic-molecular theory just says that if something's got more kinetic energy, it's moving faster, which means that it's warmer. And so we'll talk about that, why gases expand so much when you heat them, hot air balloons, stuff like that, and properties of them. So, yeah, I'm not going to spend a lot of time on any one slide. If you need to, you can pause and write down some notes on the side of your paper next to the slide if you'd like to, of anything that you think that I say that sounds important, like. So, each phase has its own properties. Gases have unique properties because of how far apart they are. They're way different than solids or liquids. In fact, it was our whole study of stoichiometry and identifying how many particles are in one mole that all came about by people studying gases. Remember how we used that 22.4 liters for 1 mole at STP every now and then back in stoichiometry? We'll be looking at that today, I think. We'll identify what standard temperature pressure is. It's something that you're going to need to memorize and know very, very well. So they're much more spread out, less interaction between particles, but they'll bump up against the boundaries of whatever's containing them to create pressure. So pressure, temperature, volume, very much a gas phase type of question. Tackle. Both have smaller molecular forces, liquids and solids do, but in many ways, gases are kind of like liquids because they flow, and they do take the shape of their container, and they fill their container totally, and they're very compressible. Liquids are slightly compressible, but they flow, and they're able to move around, so they have much more similarities with liquids than they do with gases. So gases flow. They're fluids. You've got the whole, somebody has a smell over here in that part of the room. Eventually, everybody smells it over there. Or like what I always hope for is coming in the house and smelling bacon. Like, yeah, it's bacon time. So fluid means any substance that can flow. I mean, if you turn the air conditioning on, you got gases flowing, right? They're moving through ducting. They're being pumped. They're being pushed. Okay, and then by densities and by temperatures, they're rising or falling, and you got a fan inside, and it's moving the gases around. So definitely they flow. They're relatively far apart and able to move past each other easily. They flow very well. Gases have low density as well, much lower density than liquids and solids than they do, and so they tend to rise and mix much more easily because of that relative large distance between gas particles. Most of the volume occupied by gas is empty space. But even though that's true, gas particles are moving very fast. So it's not like you'd be like, oh, I'm touching empty space, probably. No, they're far apart from each other and they're moving through that space very quickly. Low density, though, means that gas particles travel long distances before colliding with each other. But they do, and they're going fast. So you're always getting bombarded. You're always being bumped into by gas particles. You can feel that if the wind's blowing, or just move your hand. You can feel the air on. Everybody go like this. Everybody go like this. Wave your arms around. Can you feel the air? Yes, you can. Okay, there's some fun things you can do with a syringe. If you got one of those at home, you can fill it with liquid and try to squeeze it. It won't go very far, right? This is the beauty of hydraulic brakes. But if you do the same thing with a gas, you can compress it probably at least 2/3 of its total volume, maybe up to 85–90% of its volume. It'll take up a really small amount of space and be really hard to do it because you have to apply a lot of pressure to it. So you can take a gas that's this big and you can squeeze it into a space that's that big. The particles don't go anywhere, they're just closer to each other. And if you do it fast enough, you can heat your little container up. So the space that's occupied by a gas is very small compared to the total volume of the gas, and so you can get those things to be much closer to each other and squish them together. Small pressure will move them closer together and decrease the volume, obviously. A solid has a certain shape and volume. A liquid has a certain volume, but takes the shape of the lower part of its container, like it sinks, right? It stays at the bottom. Contrast, gases fill their containers and gas particles are always moving, and as I said, high speeds and are far enough apart that they do not attract each other. Like we won't have the same type of sticky forces that we'd have with liquids or with solids, and therefore a gas expands to fill the entire volume available, like a balloon. What's your favorite color of a balloon? If you were going to get a balloon, what color would it be? I would choose red, right? I would choose red any day. Though I like black balloons too. Pressure. Okay, well, let's talk about atmospheric pressure. Now, there's a picture of a Mercury thermometer Oh, no, it's not thermometer. Mercury barometer on page 419, right across from pictures of the atmosphere and whatnot on 418. You know that the higher that you go, like Matthew, when you become an astronaut, further up you go, the less resistance there is going to be for your spaceship, right? Because there's less air particles to bump into. Isn't that fun? It's it's fun. I'm telling you, it's fun. So, yeah, Earth's atmosphere is commonly known as air. It's a mixture of gases, mainly nitrogen and oxygen, but lots of other ones too, but just in trace amounts. You cannot always fill air. You may have thought of gases being weightless, but all gases have mass. If you watched Mark Rober's thing, I guess 2 weeks ago, he did a thing. I'm like, do you weigh more or less if you toot? Yeah, so you might want to go watch that, figure out what it is. You know, it's kind of fun. I mean, knowing about it, not tooting. You know what I mean? Um, the particles in the air are attracted to the Earth by gravity, but the further away you get, the less attracted they are. And then the ones that are lower down have more air pushing down on top of them. Same thing with you. As gas molecules are pulled toward the surface of the Earth, they collide with other ones and create air pressure. So there's more air pressure at lower elevations, more air pressure at lower elevations, less air pressure at higher elevations, like if you go up to Denver or something like that. That plays into why high altitude it takes things will boil at a lower temperature, things like that. There's just less pressure, or why your ears pop when you're changing altitude. The density of air changes when you change altitude, and the atmosphere is denser as you move closer to the Earth's surface because of the weight of atmospheric gases pushing down on you. Can you feel the pressure? Can you feel it? Maybe not. The first barometers, which is the thing that measures pressure, were made with mercury. You've got a compressed bit of air at the top of that tube there. The air can't get out because the mercury is in the way. And then as air pressure is pushing down on the surface of that mercury, it's forcing some mercury up that tube and compressing that bit of air at the top of the tube. They would then measure if there is more push down there, the pressure is higher, like when you have warmer temperatures during the day. More push down on that thing will go up higher. It will compress that air a little bit more, and they would say that the mercury is rising. Mercury is rising. Low pressure, a storm comes in, less pressure on that thing, and so the pressure is released. There's less pressure on that column of air, and it expands, and the level of mercury goes down. They would then measure that on a stick, and we would measure it in millimeters. How far up this certain size of a tube the mercury would go up. Okay, so they talk about that even today. If you're listening to the weather report, they'll talk about the mercury going up or going down. They usually though measure that in um, millimeters or inches. So 30 inches mercury is more common than talking about a certain number of millimeters, or like 760 millimeters of mercury as our standard atmospheric pressure. Just saying. So it really does depend on the circumstances as to what kind of pressure units that you're measuring things in. Like I said, for weather, they're going to talk about inches of mercury or millimeters of mercury, though, because you got lots of increments that you could do to show how much things are changing. With bicycle tires and things like that, it's usually pounds per square inch, or PSI. You also have pascals, or you have atmospheres, or if you do some like English engineering, you get things like the torr, Torr. Technically, in physics and math types of stuff, pressure is F over A, force divided by surface area. And this is why we can get boats to float, things like that. amount of force divided by over a certain area's pressure. This is also why people can lay down on a bed of nails, right? So to find pressure, you need to know the force pushing down on something in the area over which that force is exerted. You can get ice to melt if you hit it really hard, or push down on it really hard. Units of force in the SI system are newtons, and then we've got square meters for area. So yeah, I got what a newton is. It's a kilogram times a meter per second squared of acceleration. It's kind of a weird unit. But if you've got a newton divided by a meter squared, you've got 1 unit of pressure called a Pascal, named after Blaise Pascal, the French mathematician, theologian, scientist guy who did a fun experiment. So he had a barrel and he had a little tube going into the barrel, and he would pour water down the tube into the barrel, and he could get the barrel to pop if he put enough pressure on it with his column of water from like the second or third story. So it got named after him, Pascal, the PA. 1 Pascal is 1 Newton divided by 1 square meter. It's very, very small, so usually they talk about kilopascals rather than pascals. Talk about them in terms of thousands of pascals. It is 1 Pascal is the pressure exerted by a layer of water that is 0.102 millimeters deep over an area of 1 square meter, so that's like nothing. Atmospheric pressure can be measured by a barometer. The atmosphere exerts pressure on the surface of Mercury in the dish. We already explained that. So there's your Mercury barometer. And typically, if you got a normal atmospheric pressure, the mercury will go up the tube 760 millimeters. So that's, 0.76 the way up a meter stick. So it's not a really big diameter on that tube. And then again, it's that little bit of air at the top of that thing that's being compressed. Or actually, that says it's a vacuum. It's a vacuum. At sea level, the atmosphere keeps the mercury at about 760 millimeters, or its equivalent 1 atmosphere. 1 millimeter of mercury is also called a torr, after Evangelista Torricelli, the Italian physicist who invented the barometer. And studying the effects of the change of temperature and pressure on a gas. Oh, that was weird. One will find a standard for comparison useful. Scientists have specified a set of standard conditions called STP, which I guess could stand for Stone Temple Pilots, or standard temperature and pressure, or what else could STP stand for? Sticky toilet paper could stand for that. But in chemistry, STP is made up of 2 quantities that we want to control, and if we can set our temperature and pressure to these particular things, then we can all talk the same language about other things like volume, amounts of things. So if we set the thermostat to go to 0 Celsius, which would be pretty cold, and 1 atmosphere of pressure, then we can do our experiments and know from off of a chart exactly what volume conditions we should experience with gases and things like that, how many things there would be in that volume of gas, number of particles. So SDP is 0 Celsius and 1 atmosphere, and don't you ever forget it. Okay? Don't you ever forget it. Room temperature is like 25 Celsius, so we have to make adjustments in our calculations. If the pressure is different or if the temperature is higher or lower, then we gotta adjust our magic numbers in our charts tables. But here's our go-betweens on things. Here how everything is equivalent. Atmospheres and pascals, and then how bars relate to pascals, and how millimeters of mercury compares to pascals, and how pounds per square inch or PSIs compared to pascals, and how torrs compared to pascals. And so if you're curious about some of these, you're gonna go onto your calculator, and I'm gonna just clear this thing out, and you're gonna go to your apps. And remember that Science Tool thing, that Science Tool app? Okay, once you press a key, it's got significant figure calculator, and then the second thing on there is a unit converter. Okay, a unit converter is going to be your friend here, and you see that number 9 there is for pressure. So I prefer, if you use this thing, to go between these various kinds of units: pascals, kilopascals, bars, millimeters of mercury, millimeters of water. Sorry, first the millimeters of mercury. Then you got inches of water and inches of mercury. That would be how they would do it with the weather: 30 inches. You got pounds per square inch, so that lb/in squared is psi's, and then you got atmospheres. So you can go ahead and say 1 and then choose pascals and then see what that is in atmospheres, and it'll do the conversion for you, which is equivalent to what we've got somewhere. Well, actually, it's not one that they show in the book, right? So let's do 1 atmosphere, and we'll convert that to pascals. Yep, that's the same number we got there in the book. You're an ugly bird. Just use your calculator as you're doing sample problem A types of problems. I asked you to do numbers 1 through 4 on page 421. Just use your science tools on your graphing calculator. Okay? You're welcome. Not going to do the sample problem. It's really easy. Okay, last thing on the last page, kinetic molecular theory just says that if you heat things up, they're moving faster and then bump into each other more. Model that used to predict gas behavior, and it's good theory. It's still theory though, because it doesn't predict everything. And there's a thing called ideal gases, and then there's real gases, which follow some pretty complicated formulas. There's been some number file videos about those recently, about fluids in general, but I forget the name of the theorems. A set of 3 differentiable equations that they use to try to predict the motion and behavior of things like gases, which are really complicated and randomish. Nevertheless, kinetic molecular theory states that gas particles, Navier-Stokes, that's what it's called. Gas particles are in constant rapid random motion. The theory also states that the particles of a gas are very far apart relative to their size. This idea explains the fluidity and compressibility of gases. They can easily move past one another or move closer together because they're farther apart than liquids or solids. Gas particles in constant motion collide with each other and with the walls of their container, creating pressure. Theory states that the pressure exerted by a gas is a result of collisions of the molecules against the wall of the container. I just said that. The kinetic molecular theory considers collisions of gas particles to be perfectly elastic, which is pretty close to what you experience because they're so small. But the larger the gas particles are, the less perfectly elastic that gets. Energy is completely transferred during collisions. The total energy of the system, however, remains constant. Average kinetic energy of random motion is proportional to the absolute temperature, or temperature in kelvins. So in the next section, as we introduce the gas laws, we will be operating in kelvins, not degrees Celsius. And we'll be doing it in atmospheres, not some other type of pressure. We need a 0 standard somewhere. And kelvins are going to be the thing. Okay? Heat increases the energy of random motion of a gas, and not all molecules are traveling at the same speed. We'll talk about that later when we talk about 2 gas mixture and which one, if they're leaking out of a hole, which one will go faster. Maybe we'll talk about why your voice can be high with helium and low with barium hexafluoride or whatever it is, the one that makes your voice sound really low. So there is a curve here that we're talking about. For a 10 degree Celsius rise in temperature from standard temperature pressure, the average energy increases about 3%, while the number of very high energy molecule approximately doubles or triples. So hot gases are super chaotic. Got a little thing here to explain that. And way over on the right side of the picture, they measure the error, the absolute error between the two. That there's a little fudge margin there that it makes gases a little bit harder to work with and a little bit harder to predict their behavior, but we'll get something that's close enough and gives us good approximations for these things. Yes, okay, that's the end of that section. This is the boring section. The other ones to me are much more interesting. The math is pretty straightforward. And yep, so you've got a couple, actually you got 4 practice problems to do and some work out of your study guide. Also remember to go watch Matt's slideshow and watch the little video of the guy shaking the stuff up and making it different colors with vanadium, a very cool element. Also for Friday, you're going to watch Smarter Every Day episode 113 as he drives around with a balloon in his car. You might want to try that at home. Yep, there you go. There's 26 minutes of your life just, down the flusher. Okay, stay safe, everybody, and stay thirsty.